Hello and welcome to The Space Above Us, Episode 64, Backbone of the Shuttle, External Tank, and SRBs. Last time, we took a quick look at some of the historical forces that led to the creation of the Space Shuttle as the focus of NASA's human spaceflight program in a post-Apollo era. We learned about what NASA's ambitious plans were, what reality had in store for them, and how they were able to work out a political deal with the help of the US Air Force. But what we didn't learn was what sort of vehicle actually emerged from all that wrangling. There wasn't an obvious answer to this difficult question, and there were a lot of different ways to come at the problem. There were exotic options, like the Liquid Air Cycle Engine, or LACE, which pulled liquid oxygen out of the air as it ascended, requiring only fuel to be carried on board. If such a mechanism could be made to work reliably, it would offer enormous weight savings, and thus allow smaller vehicles with more payload. There were incremental options, like just adding wings to the first stage of a Saturn V. Ideas like this might help a little, but basically we're just continuing with the same old expensive options with a few minor tweaks. And there were flat-out strange options, like the Chrysler SERV, which I have affectionately dubbed the Space Onion. Because who said a 70-foot-tall, onion-shaped launch vehicle covered in aerospike and turbojet engines couldn't work? Not Chrysler, apparently. The research said that the best long-term solution would likely be a fully reusable system that both took off and landed like an airplane, horizontal takeoff and horizontal landing. But that same research said that it would also be the most difficult approach, therefore costing the most in the development phase and reaping the savings later during flight operations. Programs that cost a lot up front, based on the promise of savings years and political terms down the road, are tough to get funding for. They also require a lot of flights to make up for the development costs. And while NASA had big plans, nobody was really sure what sort of launch tempo was going to be feasible. It was possible that they could spend a lot of money on a massively expensive reusable system only to fail to realize their savings when they couldn't keep up the pace. So the goal was to get off of fully expendable systems, but a fully reusable system was seen as overreaching, at least for now. As is often the case in engineering and project management, the answer that was arrived at was a compromise: a two-stage, partially reusable vehicle. Alert listeners may remember that last time I mentioned the shuttle's stage-and-a-half design. It turns out that I got my space fact wires crossed and was maybe pining for the days when all this stuff was a little simpler and easier to fit in my head. That's because the Atlas rocket, used back on the orbital Mercury flights, was a sort of stage-and-a-half vehicle. The whole thing went to orbit, but along the way it dropped two of its engines off the side to save weight. Whoops. One idea that emerged from the partial reusability concept was that of a disposable external propellant tank. The idea here is that a rocket needs a lot of fuel and a lot of oxidizer, but it only needs it on the way uphill. Once it gets to orbit, any volume it used on storing propellant is just taking up space and making re-entry and landing more difficult. But while spacecraft are pretty expensive, fuel tanks aren't. I mean, a fuel tank the size needed by the Space Shuttle wouldn't be chump change, but compared to the overall cost of the system, it'd be pretty cheap. So why not keep the fuel in a big tank next to the spacecraft, ditching it once we make it to space? If we combine this idea with some of the requirements we discussed last time, we start to get pretty close to the final picture. The orbiter, the actual spacecraft, would be a sizable vehicle with a 60 by 15 foot payload bay and large delta wings. The whole thing would be mounted to an external propellant tank, providing fuel and oxidizer to some liquid-fueled engines. The entire stack would launch vertically, with the tank being discarded once orbit was achieved. The orbiter could then do its mission, re-enter, and glide back to its landing point, while the external tank tumbled to its demise somewhere over the ocean. The only sticking point here is that while the planned engines would be incredibly powerful, they wouldn't have the strength necessary to lift the entire vehicle off the pad. Something else would need to get the ball rolling. As far back as World War II, planes that were either too heavy or too needing more runway to take off on their own were fitted with large solid rocket motors called JATO, for jet-assisted takeoff. Remember, this is back when rockets were still called jets for some reason. The rockets didn't burn for long, but they imparted a big burst of speed that allowed the planes to get off the ground. NASA decided to go with a similar concept and strapped two massive solid rocket boosters to the side of the propellant tank. They wouldn't go all the way to orbit, but would provide the power required to get off the pad and above most of the atmosphere, where the liquid-fueled engines could then do the rest of the work. Alright, so what have we got? We've got a winged orbiter attached to an enormous external propellant tank that fed fuel and oxidizer to liquid-fueled engines. And attached to the external tank were two giant solid rocket boosters. If this is starting to sound familiar, it's because this is, in fact, the final configuration arrived upon for the Space Transportation System. Let's take a look at each of these components in more detail. I know I've been a little heavy on meta show details lately, but I've got another quick one. Something I've been struggling with is how to ingest the staggering complexity of the Space Shuttle and transform it into something easy and entertaining to understand, something I like to think is a hallmark of this podcast. The challenge is that when it comes to the shuttle, there is a lot. I could probably do another 10 or 15 episodes on the various subsystems before even getting to the first mission, but I think that would be boring and frustrating. It would also basically require me to quit my job and study the Space Shuttle nonstop. Instead, I'm going to try to weave most of it into the main mission episodes as we go. I only mention this because today's episode is going to be a little high level, and I didn't want people out there saying, "But JP, what about the anti-geyser line or the frustum flotation device?" I know. I'll get to it. I promise. 135 missions will give us plenty of time. Also, I just want to point out that this episode has a lot of numbers. I'm using reference material from the early Space Shuttle program, so a lot of these numbers might be different from modern numbers you might find. For instance, the external tank went through several revisions that made it significantly lighter over the years. I'll try to call those out as we hit those revisions, but for now, let's just cover the baseline. Alright, back to business. Let's start with that big external propellant tank, creatively dubbed the external tank, or ET. The ET is a large aluminum cylinder with a dome on the bottom and a tapered point on the top. At just over 154 feet long and 27.5 feet in diameter, it's easily the largest part of the entire system. Inside, it's actually two tanks on top of each other, one for liquid hydrogen and one for liquid oxygen. At the very top, there is a spike, which, perhaps with Apollo 12 in mind, serves as a lightning rod during ascent. This is also where you'll find the venting system for liquid oxygen that is boiled off during the build-up to launch. We'll talk more about pad structure later, but you've almost certainly seen the gaseous oxygen vent arm, usually called the beanie cap, that sits on top of the ET and slurps away any vented oxygen until moments before liftoff. Below the big spike on top is a 53.5 foot tall liquid oxygen tank. Since the whole structure has to taper to a point, it's got sort of a complicated shape, made up of a dome on the bottom, a short cylinder in the middle, and a shape called an ogive on the top. Ogive apparently just means tapers to a point, by the way. Vocab of the day. The tank holds 143,000 gallons, and since liquid oxygen is pretty heavy, it tips the scales at about 1.3 million pounds when full. The weight of the liquid oxygen also means that the interior of the tank needs a bunch of baffles, which prevent it from sloshing around. If it started sloshing in the wrong way, it might build up a resonance, and that could make the whole vehicle impossible to control. Below the liquid oxygen tank is the liquid hydrogen tank, which gets to be a more normal shape, just a giant cylinder with domes on either end. The tank is 97 feet tall and stores 363,000 gallons of liquid hydrogen. Just to give you an idea of how much that is, if you wanted to store that much hydrogen using the typical sort of tanker truck you might see on the road, you would need 40 of them filled to the brim, and you'd still come up a little short. Since hydrogen is so much lighter than oxygen, the fully fueled liquid hydrogen tank actually only weighs 226,000 pounds, about 6 times less than the fully fueled liquid oxygen tank, despite having 2.5 times more volume. And because of that relatively low mass, no anti-slosh baffles are required. However, there are some baffles near the bottom to prevent the fuel from swirling around the sides and leaving an empty space in the middle. These anti-vortex baffles are actually placed in both the hydrogen and oxygen tanks. In between the two is the intertank, a 20-foot high cylinder that connects the two tanks. The intertank is a handy place to mount some instrumentation, access ports, and reinforced plates for the solid rocket boosters to attach to. It also creates a space for the upper dome of the hydrogen tank and the lower dome of the oxygen tank, doing away with the need for the tricky common bulkhead design of the S2 stage on the Saturn V. The exterior of the tank is covered by a spray-on insulation of varying thickness. The insulation protects the aluminum skin while the shuttle is out on the launch pad for weeks at a time. It also protects the orbiter, since without insulation, ice would form on the tank's exterior when it was filled with super cold propellants in that muggy Florida air. Remember all that ice that fell off the Saturn V when it lifted off? That's fine when there's nothing below you, but with the orbiter strapped to the side, that would be no good. The orbiter is designed to handle the rigors of launch, orbit, and entry, but not stuff falling off the structure and hitting it. Fun fact, for the first two launches, the external tank was white, since paint was added to protect the insulation. After the first two launches, they realized it wasn't necessary and decided to stop sending several hundred pounds of paint into space, giving us the burnt orange color we're familiar with today. Altogether, it weighs about 80,000 pounds when empty and 1.6 million pounds when full. Both of these giant tanks fed their propellants to liquid-fueled engines via their own 17-inch wide pipes. Liquid oxygen was delivered at 16,800 gallons per minute, and liquid hydrogen was delivered at 42,000 gallons per minute. Come to think of it, we haven't really mentioned much about those engines. Normally, rocket engines would go on the bottom of the tank, but we're going to be throwing this tank away when we're done with it. So how about we move the engines into the back of the orbiter? That way we get them back at the end of the mission. Sound good to you? Great. Oh, and for the metric-minded out there, here's some quick, slightly rounded conversions for you. The overall external tank is 47 meters tall and 8.5 meters in diameter. The oxygen tank is 16 meters tall with a volume of 540,000 liters and a filled mass of 616,000 kilograms. The hydrogen tank is 30 meters tall and 1.4 million liters in volume and has a filled mass of 102,000 kilograms. The whole thing is 35,000 kilograms when empty and 756,000 kilograms when full. The propellant feed pipes are 43 centimeters in diameter and deliver oxygen and hydrogen at 64,000 and 171,000 liters per minute, respectively. Flanking the external tank were the two solid rocket boosters, or SRBs. Standing at 150 feet tall and 12.5 feet in diameter, they were then and remain in 2018 the largest SRBs ever flown. But wait, I hear you asking, what is a solid rocket booster anyway? A solid fuel rocket is just a rocket that uses solid fuel instead of liquid fuel. You've probably actually handled one yourself, albeit at a much smaller scale. Ever light a bottle rocket? That's a solid fuel rocket. When the lit fuse reaches the body of the rocket, it ignites solid fuel, which for the bottle rocket is probably gunpowder and some sort of binder, which generates hot gas that is then directed out the back. Equal and opposite reaction, and off you go. The Shuttle SRBs are the same idea, but at a much bigger scale. Instead of using cardboard for the casing, it's half-inch thick steel. And instead of a sprinkling of gunpowder, it's 1.1 million pounds of atomized aluminum powder, ammonium perchlorate, iron oxide powder, polybutadiene acrylic acid, acrylonitrile, and epoxy binder. I'm just going to call all that the propellant. The propellant is poured into the casing as a goopy liquid before it's cured, which leaves it at about the same consistency as one of those pink pencil erasers. Pouring 1.1 million pounds of propellant into a 150-foot tube all at once, and worse, transporting it when cured, would be really difficult. So to help make it easier, each SRB was broken up into 4 main segments. The forward segment, the forward center segment, the aft center segment, and the aft segment. The segments were transported separately with the cured propellant already in place, and then reassembled at the Kennedy Space Center. The segments came together at clevis joint-style field joints, so called because they were joints connected in the field. We will have cause to examine these joints in great detail 25 missions from now. The forward center, and aft center segments are pretty much just the steel casing and solid propellant, but there's some special stuff at the top and the bottom. On top are a few components that don't carry propellant. The nose cap, which is exactly what it sounds like, the frustum, which is a sort of truncated cone shape under the nose cone, and the forward skirt, which is just a cylinder. If you were to crack all that open, you'd find a bunch of specialized hardware. Each booster had 4 small separation motors that pushed the SRBs away from the orbiter when they ran out of fuel about 2 minutes into the flight. In addition to the separation motors, you'd also find a whole bunch of different types of parachutes. That's because the SRBs were reusable. The external tank would be discarded and left to burn up in the atmosphere, and the orbiter would glide to a runway landing. So the SRBs split the difference. After separating from the shuttle, the nose cap pops off and deploys a pilot parachute. The pilot parachute deploys a couple drogue chutes, and the drogue chutes deploy the main chutes. The main chutes, which were each 115 feet wide, unfurled slowly to prevent shocking the whole system and gently lowered the empty booster into the ocean. Well, gently might be a strong word. It crashed into the water at about 60 miles an hour, so let's go with survivably. Once in the water, the SRB activates several recovery and location aids, and crews get to work dragging it back to port for refurbishment so it can be flown again. Skipping all the middle segments, we get to the aft segment down at the bottom. The aft segment contains a nearly 14-foot-high nozzle, which accelerates the hot gas from the back, pushing the SRB along. And as if merely surviving 2 minutes of 5,800-degree Fahrenheit gas wasn't impressive enough, the nozzle can also swivel side to side. With the help of a hydraulic-powered thrust vector control system, the nozzles can move up to 6.6 degrees, steering the massive vehicle. Unfortunately for the nozzle, its hard work was not rewarded. Shortly before splashdown, an explosive ring embedded around its circumference detonates, severing the nozzle from the rest of the SRB. This protects the rest of the structure from excessive loads during splashdown. The SRBs bear the weight of the entire fueled external tank and orbiter and convey it down to the mobile launch platform. At the base of each booster are 4 massive posts that are held in place with giant frangible, engineering speak for breakable, nuts. When the time comes to launch, commands are sent to each nut to split them down the center, freeing the booster to lift off. There were redundant command paths for each nut, since it was of utmost importance that all 8 broke at once when the SRBs ignited. Otherwise, the whole structure would torque to one side, and that would be a bad day with a capital B, capital D. And speaking of ignition, just how do you reliably light a 150-foot tall SRB? With a smaller SRB. Okay, but how do you light that one? With an even smaller one. Okay, what about that one? Actually, that's pretty much as far as it goes. When the computer sent the ignition command, a device called a NASA standard igniter lit some special chemical pellets. The pellets then lit a 7-inch long micro SRB. The micro SRB lit a 3-foot long mini SRB. And the mini SRB sent a torrent of flame down the central cavity of the main structure, evenly and reliably lighting the propellant. One of my favorite features of the SRB is how they handled throttle control. Normally, there's no such thing as throttle control on an SRB. It's one of their major downsides. They're either on or off. Once you light it, you're going somewhere fast, whether you wanted to or not, because there's no way to turn it off. It's also one of the reasons they had never been used before in a human-rated launch vehicle. But it's also trouble since a rocket typically needs to throttle down the engines a bit as it passes through the period of maximum dynamic pressure, the period when the air is pushing back on the structure at its hardest. So, how do you handle this with an SRB? The answer, as you might suspect, is pretty clever. You change the surface area available to burn. At liftoff, a cross-section of the propellant in the forward segment would look like a spiky 11-point star. This presents more surface area, allowing faster burning and generating more thrust. But by the 62-second mark, when max Q is approaching, the points have burned off and now the central cavity is a circle, which has considerably less surface area. Less surface area, less burning, less thrust. Clever. All of this extra effort and complexity is worth it because in a relatively cheap and relatively easy to refurbish package, you get a reliable booster that delivers a whopping 2.6 million pounds of thrust. Each. Good for getting off the pad in a hurry. And once again, as a favor to the 95% or so of the world who gets to use the metric system, here are some quick rounded conversions. Each SRB is 45 meters tall and 4 meters in diameter. When empty, they weigh 88,000 kilograms, and when full, they weigh about 590,000 kilograms. At liftoff, they generate 12,000 kilonewtons of thrust. The rocket exhaust coming out the back is about 3,200 degrees Celsius, their parachutes are each 35 meters across, and they splash down at just under 100 kilometers per hour. And last but not least, we arrive at the orbiter. The big white space plane mounted on the external tank that most people think of when they hear the phrase Space Shuttle. Well, I hate to do this to you, but it's gonna have to wait until next time. It seems that even my cursory look at the ET and SRBs took a little longer than I expected, and there's just no way I'd be able to do the orbiter justice with a few frantic minutes at the end of an episode. So tune in next time to learn all about NASA's new human spacecraft. Where does the crew sit? What are those big lumps by the tail? And how are we going to keep the vast underside of the spacecraft nice and cool during a fiery re-entry? Ad Astra, catch you on the next pass.